Okay. So hello everyone. I'm Yash Gupta, and our plan of action today would be we'll be first talking about how we came up to the transformers part, what the thinking went behind it, how we transitioned from one algorithm to another algorithm and reached transformers, and in the end part we'll be discussing about uh, taking a hands-on session on basic LLM utilization. So so this here is the first timeline, how we reached Google Transformer from ANN. ANN was the first dive into the deep learning part, where any model, where the computers can understand or can behave like humans. So
ANN 1943.
yes, the first when the first paper of for the ANN was developed. And
Paper for ANN.
yes, when
ANN.
it came into existence.
ANN stands for
Artificial neural network. So
But the computer came into it in 1970, right?
yes, but this theorem for
It was theoretical paper
yes,
way before computer existed.
yes. It was a basic mathematical paper on how there was a combination, a collection of researchers from mathematical background and biological background, and they were researching out how we can think or can transform mathematics into human neuron format. Okay, so let's dive into first the artificial neural network. So
Can you go back? I want to.
yes,
Go through the timeline.
yes. So after there are few drawbacks why we shifted from ANN to RNN. RNN stands for recurrent neural network. Then we came up to LSTM. We had recurrent reoccurrence.
Okay.
Then we came up to LSTM, stands for large, long, short-term memory.
Okay.
And then we came up to bidirectional RNN. What was the requisite why we required to move from RNN to bidirectional RNN? We'll talk about it. Then we came up to encoder decoder, where we started to see the development of AI as in the field of software development. Then we came up to the transformers, which is the current most powerful format of all this history past. So let's talk about the artificial neural network. This was the birth from where things started about the deep learning part. So all these connections, these are the inputs. We say that input layer, then start as the hidden layer. The main computation goes behind in the hidden layer, where each layer is connected with weights, a parameter uh, which we say as a learning parameter. We change its weight numbers, so each we can represent the input as in what impact it would play. If the weight of this input would be higher in this neuron, it will provide that out of these inputs, this will play a more impact over the R prediction model. And for better understanding of what all these are, and in mathematical computation, we can see here, this is our neural representation of biological. Now, these are your inputs, x1, x2. Now, people might ask, how are we, like, we have words, but computer can't understand it. So what we do is we convert them into vectors, numerical format, or we can say as array format. Now, these arrays, we have multiple arrays. For every single word, we have fixed dimensional array. It could be 6, 7. In transformers, we have 512 dimensional array. Now, each of those arrays are in those arrays, every single data is passed on from this input layer. Then these connected nodes are connected with weights. We change it based on our prediction. We calculate the errors and we change it. The weights can lie from minus infinity to plus infinity, but as when we initialize, the computer does not have any understanding of weights, so we initialize this between 0.5 to 0.1. We can tune as per the model requirement. Now we do all. Now this formula does all the tasks, which so that we can go from input to the output part. Now the ANN has few drawbacks. Once we have trained it for a certain sort of data, this neural network is incompatible to get to provide you with any input which is outside of that data set. So it's a static. It won't learn as we go on. And in this ANN, we also have a drawback as the input can be variable. You can have 6, 7, 8 as the words like hello. So hello would be in like 3-dimensional format. So first of that hello world, the first index, second index, and third index. It will do word by word processing. Now we can arrange, once this is there, this architecture is formed, we can add as many data set as it is. We can add as many words or data within this, but the output format is fixed. We can, as in this, we have a dimensionality of 3. We can pass on n in multiple time steps. We can have multiple inputs provided in this, but the output would be a single word. Now we can adjust it if we want to have multiple outputs. We can have multiple nodes, and each node would represent different sort of data.
So in NN, we can have multiple inputs, multiple outputs.
The
But
input
the
would-
number of inputs will remain constant and the number of output will remain constant.
Yes, but when we output, like artificial neural network, we input in this data set. So artificial neural and network would convert into three-dimensional arrays, 3 vectors with dimension of 3. So artificial vectors first index, second index, third index will pass on. We will compute it, all these weights here and all here weights plus here. Just remember that in this part, we say that input layer, but no learning happens here. All the tasks happen after the hidden layers are there. And this part of this hidden layer is why this is termed as hidden, because of deep learning's black box architecture. We cannot say after the conversion of these alphabets into what those vectors would represent. We cannot understand or visualize how are we changing it. It's very difficult to actually understand how researchers came to it, because at that time we don't have computers. So how are they able to compute, like, if you pass on this vector, these weights will change, something will happen within itself, and we are able to get what we require. We can't do any visualization of this stuff. That's why it calls as black box. It's still the case. We can, in deep learning, we cannot say what is happening within these layers. It's still a mystery, but somehow the researchers were able to come up with these things without knowing what is actually going in between. Now, this is the animation of how ANN works. So we have inputs, we have multiple layers. This will go front and back. In the front, it will learn, and then all what predicted value is and what is our final output which we require will calculate the error between those vectors. We have a vector here, we have a vector here. We'll subtract those, get an error. We will create the derivative of that at what constant, at what rate we are different from. We will have a gradient. Then we'll go back, try to minimize those gradients, and in between that gradient calculation, we have an error, but we cannot directly subtract from the actual weight minus subtracted of the required adjustment, because then the movement would be very fast within this. The jumps between learning would be very fast. The model won't be able to grasp anything. At every point of state, it would be keep on changing things. It won't have track of anything. So learning would be much longer, and in many cases it won't be accurate. So what we do is we multiply it with a small number known as R. Just go back. Yes. Yes. So out here, after the completion output, we have, it's not controlled, but we have a new small number ranging from 0.0001 to 0.01, which minimize the jump between each weight learning. For better understanding of how things work, a beautiful representation, how we input data, input layers giving the data to the artificial neural. The hidden layer calculates all the things, and the output layer presented what we are required. Now, in this case, we have 2 nodes. So what we are doing is we are doing classification, but in this case we have 2 images, but we can have multiple. The thing of this that is that we can have multiple hidden layers in between this, and plus, like, this is what we can have multiple in transformers and other things. We have n number of nodes. I actually don't. No one has ever told that what number of nodes is. That's unknown at the time. And output we can have multiple. Like earlier we had single nodes, so it will represent a single word. But here for as per the user's requirement, we can have multiple nodes. As of here, we are adding up both the data to get a better representation. Now, why are we doing this? It's basically the thinking that what the user requirement is, what our task is, what our aim is to get. This can vary. If you search ANN, you have multiple architectures that would confuse you as a beginner. So this is the basic format. The most basic format is this. Yes, this is the most basic format where we have multiple input and one output for basicity. Now this can change based on user requirement. This is the task of data scientists and machine learning engineers. Now challenges, as I told you, that it's static. Once trained, it can't adapt to new things. You have trained a data set related to technology. If a person asks that model about what is an apple, it won't be able to. It will either won't provide you with the correct input, it will try to hallucinate, or it will just straight away reject it with some jargon. Now, black box architecture, as I already told you. Now the memory. In ANN, whatever like we have in this, if we pass here artificial neural network. So once artificial is gone, we have processed all the data for artificial. Then we pass on neural. So the neuron output does not have any, the next input won't have any representation of what artificial means. So artificial and neuron, they won't have any connection. How are they connected? We don't have anything else. What is artificial neuron? It will learn. What is neuron? We know. But how are they related? So the ANN does not have any architecture to store that data as what we have done earlier. That's why we came up with RNN, recurrent neural network. So what is the difference between RNN and ANNs? Is we have a loop over here. This is the basic, and for that exact ANN, we have like, for basic understanding, we have ANN1, ANN2 stacked over each other. These are a single loop. Just to represent how the data would flow, I have represented two. So as you can see this loop will get all the data computed from the first node and into all these nodes. From each node, all the learnings has been passed on to the next time step, where each node will get the input plus the previous understanding from its previous predecessor. Now, I have represented with blue and purple for each node, but this data from the first node, the same thing will happen as it has happened with second, third, and fourth. It will be very cluttered. So I just created with two representation of how the message would be passed. Now we had an advantage that we have the data set of what happened earlier. So we have a reference of what is artificial, what is new. Now, thing is, we have a limited storage capacity as all these data have a fixed dimensionality, which once can be tuned, can't be tuned after the model is trained. Plus, because we are sharing the data, the weights of those hidden layer, between the hidden layer and between these outputs, all will be shared with here also. But the thing lies with RNN, which is that different from INN, that weights plays very important role. Even a slight difference or jump between 0.1 in RNN can cause a huge jump, and the model won't be able to train. You need to train it again. The task for 1 hour could last from 10 hours, 5 hours. So basic major conflict with RN was that the weights used to shift highly. So the model is unable to train even how many times you train it perfectly. As I told, the memory is a challenge, as the the thing is also that these memory, once we have time step 1, we have inputted, the memory is calculated. Now we have time step. Next time we have time step 3, 4, 5, 6. Now the time data calculated at time step 1 will have a less impact on the time step n, 4, 5, 6, and have a more impact from the time step previous to it. So this was a drawback of RNN. Resource and also you can see that there is no parallel processing until the time step 1 has come up. We can't go to time step 2. We can't parallelly process time step 1, multiple inputs, 1, 2, 3 parallelly, and then combine all of those in the RNN architecture.
How does this work with speech recognition or language prediction?
So ANN is fixed. We can't, as a human, we have continuous words that represent something which has sentiment. You can understand what does artificial neural network or RNN recurrent neural network actually means. You can't understand recurrent. Recurrent means reference. Neuron in a graph, the basic node. And network can be of any type. But artificial neural network or recurrent neural network, when it combines, forms a new sentiment. You can understand it's different from telephone network. That's why. So that's why the RN came into play. We are able to understand the continuity. We are able to understand what word will come before that word and after that word to get a basic understanding of how humans present. Now there are some key applications. We have seen time series prediction, like for stock market prediction. We have previous year data and we can input today's data, if and then we can get the output of tomorrow's prediction.
So this
Yes.
application means that this is an inception of speech recognition, right? The recurrent neural network as opposed to advanced neural network.
Can you
I mean,
elaborate?
like this is where speech recognition started.
Yes, because we had the memory of how things are.
So it might have evolved naturally, like with LSTM and everything, but
Yes.
it started, the application
Yes,
started.
because we had a memory of the past, so we are able to have sequential.
This is the story. This is where it
This
started.
is my
Yes.
this is when,
Yes.
But
Our Google keyboard is the best example for speech understanding.
what I'm trying to understand over here in speech recognition is like you start speaking,
Yes.
it takes the input.
So the thing is, it's already trained. So it in the space of data where multiple points are there, it has its own path at the point of training. On that part, whatever data points it gets, it will try to predict that.
But not what I'm speaking, it will try to figure out from that
Yes,
word
yes.
what is this word
Yes.
based on the trained data.
Yes. When it's trained, these things would represent something. The weights, W, and the learning parameters, the things which change with everything, will represent. Imagine a 3D space, multiple points are there.
But why does it need the previous layer? Like why was speech recognition in recurrent neural network? Like it's a one-time thing. Na? You are giving one input, you're giving one word, it is a one output.
Yes.
So you're giving one word as a
So in
a
case,
format. Yeah.
just for simplicity, let's take an example. I went to the Apple store. Now I went would mean something. Apple could be a fruit, or could be technology, or the technological thing, and go. Now these things, words separately are means something else. But when combined, it means something else. I I like I like to use Apple. So we are able to understand that like to use Apple in this context. We will have the Apple mobile app technology device anything, but the computer is unable to understand. It does not know our language. We need to teach it what things come after, so it can create a pattern, can understand a pattern within those numbers. It's not playing as in words, it's playing as in numbers. So in order for it to have its pattern recognition, it will recognize this is there, so it might be this.
Okay.
So it will only happen once you have trained, and if you have trained these data set on the like technological data set, then it won't be able to provide you the correct answer for anything outside. If you ask about vegetables, it won't be able to, because it's not trained on that. Yes.
So, like, when we are talking to the AI, basically it converts our speech to text, and then its output gives text to speech. Does it
No.
work like that, or?
Yes, there are few steps in between it. When it recognizes our speech, it converts into text. Then those texts are converted into mathematical numbers, range could from anywhere to anywhere. Then we use the computation similar to here for the ANN part. We use this communication between this we get a pattern within this 3D space, a line is formed like a graph representation. And whatever the you represent or the text is, it will try to point out at that graph. And then based on its learning, which is the graph created, it will have a transpose and get you the value which is based on its data set. It cannot provide you with everything, but it will try to predict the best suitable based on its training data set.
Now, like, how do it make sentiment? Like, okay, one sentence you can say based on your tone, it can mean like, okay, you are angry, sometimes it can mean you are sad or something.
So that is classification.
How does
Yes,
that
that is also applicable. So we have to train it. It can't understand the how our basic sentiment in the form of when we speak vocally. If we are soft, it means calm, but it won't be able to that. But it can provide you with positive and negative. Like it is applicable in review analysis, where the person is happy or not. We train it on the data set where multiple we can say reviews are there, and with the each review we have an output attached to it. Like when we pass on this data set as I like that product, so in the output layer we will get some prediction. Now we will tell the model whatever we have predicted it's incorrect in the training stage, and then provide the correct input. Now based on that correct input, the mathematical number, it will change all the parameters. Now when you go again, it will provide you the correct answer. Then we will do it multiple times, and it will create a path that would be suitable based on your input. So basic understanding is we have a box, multiple data points are there. Now, based on this computation, we will create a line or a stream, cover some area, and all those data projections will be taken on that part to provide you what we are actually thinking. Now, RNNs, as I told you that we can have multiple inputs and can have single output, multiple outputs. So this is how these are the types of RNN. In the first, we have one-to-one means we have one input node. We can have n numbers of hidden layers. That's not important. These are the hidden layers are not as important as input and output, because you provide an input, how in what format you want to get an output. This is the simplest format where you give single input and you will get a single output as per the prediction. Now in one-to-many, if you want to predict like stock market prediction, what could be the range, and your model is trained, you have provided an input today's data set, what all the data is there related to that stock. It will process, provide you input based on that input, that this could be the range first, next, second, and then third outputs could be there. This basically depends on what are your use case. You can't implement all of this on your specific task. It needs to be task specific. If you are using review analysis, so you will use one-to-one, or many-to-one could be your also answer, where you can provide multiple inputs, multiple reviews, and want to get what is the correct representation of that, whether it's a positive sentiment of the user or a negative sentiment.
And so in one-to-many, as per the diagram, this visual diagram, you
Yes.
give an input.
Yes.
There is a black box of n number of neural networks that is in
Yes.
the hidden layer in the between. You get an output.
Yes.
That output will act as an input
Yes, because it's a recurrent layer code. So
for the next one.
yes,
Similar to this one.
see, in every neural network part, we will get an output, but when in this case, we don't need this. We will neglect it
Okay.
because our data set
We
is
just need the base.
like for recurrent neural network, we will pass recurrent. At that point, we don't need that output because we want the full meaning of recurrent neural network. So first recurrent will pass, we'll get some output we don't require. We will pass neural, we don't need it. In the third center, we'll pass network, and in that point, we are actually want the data from all those three previous interactions with the model. We don't need the only understanding from recurrent. What does the model understand? We don't want that. We want recurrent, then neural network understanding, so we can get a proper understanding of what it is.
So, that is basic reference.
Yes.
It is the training phase, right?
Yes.
It is not the inference.
In inference phase also, the thing would be same, but in inference phase also the things would be same. Just these learning parameters, the weight won't change. The representation or the the graph won't change as per your input. It will stay static.
Will change during only fine tuning.
When
Yes,
we are
when it's
trying-
learning.
Then when it is set, you just give input and based on that weight, it will just give the output.
Yes.
It's the same.
But there can be n number of
Time step.
recurrents, and
Yes.
it will use the weights from multiple timestamps
From its previous.
from the previous one.
And the thing is, it will have more impact from its previous than its previous older mode. Basic understanding, this is what would be. Hide those view nodes within this layer, and this will what will happen. You provide recurrent will go there, process something, and some output will come. But we don't require it within the meaning of recurrent neural network. But for your
Pass it again.
yes, then we will pass another time step. So we have the model would be static because if we try to change based on our every single input, it won't perform good, and also it would be termed as cheating. Because at that point of time, you want to pass whatever data, it will give you correct result. But when you try to do multiple tasks related to the same document, it will create incorrect predictions. So challenges we have discovered. Now RN types. So for those many to many and these two, a bit different if you see. We are providing,
Can you cover the many to one?
okay,
You're giving multiple inputs.
Yes.
And you're saying that it is Google search image.
yes. So this algorithm is used for, by Google search parallel technique, architecture, where it provides multiple images
Okay.
and provides what's the basic understanding it gets. You will provide multiple images of cats. And so it would be learned, yes, this is a cat. So it won't be applicable to every person's need. It is highly very subjective to your use case. All these things are very subjective. We can't use same architecture on our data set on other person's data set. We need to understand what is their requirement, how the form data should be there, in what form of in what form the prediction is required. Now in these two menus, you can see the output we are providing input, and each input stage after processing we are getting output. Like earlier we were trying to neglect the output, but here we are accepting it. And now in these two, we are providing the input and getting the output within those groups. But out here in this menu, we are providing a time step 1, 0, 1, 2, 3. We are providing the input, but we are not accepting. We are sending it for the further processing and getting the input output from the other nodes.
So what is the name entity recognition and machine translation like?
So a machine translation is what we say a normal understanding of
So
language
it will
translation.
reframe the sentence in that particular, like I said something in English.
Yes.
I cannot
Yes.
exactly translate it in
Yes.
Gujarati.
Yes.
The above version will do that. It will
Yes.
exactly translate word by word
Yes.
in Gujarati, but the below one would analyze the sentiment of the sentence, and then based on that computation in Gujarati, it will reframe that in Gujarati.
Yes. The function would be same. The basic, the code base would be same. But when researchers tried to implement this, they were not available getting the required result. So they tried tinkering and they got this model which is more suitable for these tasks. Basic is the previous RNN, and we have created multiple versions. We have a human mindset of playing with things. We tried the one way, it wasn't working fine, so we tried another way. We tried mixing up the things, and we got a better result in this format. So these are the present things, the present types of RNN which are applied. But for basic understanding, this is the most basic which we can understand. Based on as advanced we go, our requirements change, we can use, and we can create more also of certain in many to many, as we have like first input and then output. We can have similar format in one to many also, like we provide one input at every step and get the output at the later stage. So these are things which we can change in the future and based on our requirement. Now we came up to the LSTM, long short term. In RNN, we cannot hold the data from the past data sets. If we have a huge data set, we have a paragraph to understand. It would be able to get the data from its previous sentence or previous word, but won't be able to provide you correct implementation of the first line of that paragraph. So that's why we created LSTM. So this is a block diagram representation of RNA itself. If you see input, we get an output, we don't require, then we pass on again. So thing is same, we are just repeating it again, creating a chain. That's representation if we transform to LSTM. This is how it would be. In RNN, we have a single node that contains all the data, the previous understanding learnings, and then pass it on again to itself directly, reappears. But in LSTM, we have two. One is our cell state and one is our hidden state. The hidden state will have the data as the RNN has of the more impactful data from our previous state. Whereas cell state will contain the data, as you can see, there's less number of changes than before.
When you say more impactful data,
So-
how does it know which data is more impactful?
The weights.
So based on which data,
So-
there was weight variation.
Yes. So see,
So based on,
this is an input. This weight will simplify what is in. If the weight is 100 and these are small weights, 2, 3,
then, okay, then.
then you multiply it, create the summation. The impact of this node would be more in comparison to others. It's more mathematical. We can't implement our understanding of how we understand language. So it only plays on maths.
This data will be hold on for the next one in the current.
Yes,
data
yes,
thing.
yes.
Okay.
We pass on the learnings, whatever the data is. We have learned whatever the projections we have made in the graph.
Okay.
So this is what this will be in every single node. Things would change, but the architecture will change because these will be constant. You will have input into weight assigned to here and then a bias. And then we will create, now at this point, we can multiply and add and the numbers would change. So we have a distribution of data of certain sort. Now we multiply and change, the data could shift. So that's why we create bias and activation function, which regulates our data. As you earlier said, these data can vary from where to another. Like if we control the weights from 0 to 1, assume, then if you multiply with input can be of any sort. We can still have input in various format. But there are other things, but for basic understanding, weights, inputs could be of any sort of length, weights could be any sort. So in order to regulate it from -1 to 1 and activation function, then why are you converting from -1 to 1? There are other ways also. There are other activation functions also available, which might convert from 0 to 1 and other things. For here, we are using ReLU activation, which for damage function, which convert from -1 to 1. We can use different, there are multiple variations, but which fits your requirement is the best. There's nothing best as in general format. Right. Now, so let's go beyond. Like now, let's see the how LSTM actually what are the internals of it. So I've actually used the mathematical representation for better understanding this. It's a bit little complicated than RNN and ANN. So first of all, let's see what are these, the high level part. So OR gate, input gate, and output gate. So what is it task? The HT-1 will bring in the data from previous state. CT will contain the initially it will be empty, and all the CT, HT, and F1, IP, CT cap, and all these code will have same fixed dimensionality. This will also cause a drawback because and we move on to another model, and I will tell you what the drawback was. So we will first get the input and our previous state, combine it, vectors 1 and 2 will submerge it, concatenate it, then pass on the input. Now the work of forget gate can be represented here. We pass on the data, we have a ReLU activation function, we get the FT. Now FT is represented as out here is 0.8, 0, and 0.5. This would represent something we don't know, that's why it's called black box. So now the data is again to be what we say another function. Now here we do point-wise multiplication. Vector 1, vector 2, vector 1 node to vector 2 node, directly multiplication, straight multiplication. So from FT, you can see in CT, we have some changes from 0.8 to 0.9. The weightage, whatever this represents, is as gain, whereas this part has also changed from 0.0 to 0.5 has changed to 0.3. basic computation have changed the impact of every single word. Now, in that case, whatever the thing it was representing, it has gotten forgotten. We don't know what we have eliminated from our main data set. The larger, which contains the more data from the, we can say as large data, which is from the previous and previous states, whereas HT is simpler from the RNN. Now we come to input bit. We have forgotten something. Now we might need to input something also. So this node, this part, for simplicity, is
In the forget one, I
Yes.
see the formula about, like, we have done the vector multiplication
yes,
basically.
yes,
So that is vector multiplication and then it goes to the input.
yes, the same data set. Yeah.
Okay.
So now we get the CT from here and get. So for the basic, this what is it doing is we apply the function and calculate all the data with CT. Now at CT we get some sort of data similar to here. Now this part will what do is calculate a similar vector, but what it will do is it will calculate what percentage as a number from 0 to 1 will multiply and calculate how much of that data needs to be passed on. If similar to here, if we have this form of data and we assume that it's CT cap, if we multiply both those things, we will change the numbers. What will it represent from 0 to 1? That assume it's there 0.8. What does it represent? That IT, that whatever the CT vector is we are getting, out of that 80% of data needs to be updated. Similar to here, if it's there, it will say don't update it, not required. So it will calculate what percentage needs to be updated, and we will calculate whatever the thing, understanding is here, out here, and it will calculate percentage what is required. Then we will do the point-wise addition of the vector with the CT state, and now we will update our previous memory, uh, our HT memory with the previous state, and this HT will be our output. So as you can see, we have provided the input. If we see as a basic or in broader view, this part would be our adding. Then this part. Now what we are adding is CT, which contains a larger impact of the previous data sets, holds the old data sets, and add it into our present short-term data. So this holds a long-term data, this holds our short-term data after every single LSTM block. That's why it's called a long short-term memory. This is long, this is short, and this is memory storage format. And for someone who's like to know what the calculation went behind, so I added it because it was a bit complex for understanding for me also at the first time when I was understanding.
If I see the flaw correctly that you're talking about, when we don't have HT minus 1 and CT minus 1, this will have the zero vector, so the forgetful impact will be very high, and we won't be able to calculate appropriately what should go next.
Yes, as an illustration, we can, in some places, we don't imply 0, 0. As in banking data set, we apply -9999 instead of empty or 0. So it will depend again on your use case, but it is the basic data set, basic understanding. In slide set, it is 0, 0. And it will change as per its learning. And our output will be HT, not CT. CT will be our long memory, which will influence our short memory of what all data set we earlier had. Now, as I told you, data size. Why? Because all these parameters are fixed dimension. IFT will have fixed dimension to CT, HT, everything will have fixed dimensionality. Whereas CT is a long memory. It needs to hold more memory, but this dimensionality is fixed. Now, you might say, let's change the dimensionality, but if you change all this function won't work. We have vector point-wise, so vector size needs to be similar. So we can't do anything within this architecture. Now, this is also computationally expensive. As you can see, there are multiple gates, multiple nodes. Computation would be a bit difficult and take much longer. Now, if we have data set in TBs and how much large data set, and if you compute this for a single analysis, it won't take time, but for learning a large model, it will take days to understand what things are, and we will keep on learning what are the parameters. And this also, in this learning, will also go back front, calculate the output, analyze with the output which we want and calculate the error and then update all these weights. As you can see, all these weights are present in every single, and weights will affect whatever data is here. It will increase its presence and decrease its presence.
To give an example, like who is using this as of now? Short-term, long short-term memory RNN.
So we can use it in our Google keyboards. As of current, who are using most of the peoples who are already shifted to transformers and things. There might be few who might be using it, but as of current, I didn't check into what.
Who used it? Do you have any information on that?
Every person who was in that within this time frame when the LSTM was there. Yes, this was the most high-tech technology at that time after RNN, ANN. This was the one which everyone was using for best, like for analysis, whatever the RNN was doing, it was doing better. And out here, the weights are much more controlled because of this controlling function. ReLU, what does it controls limits from 0 1 to from ReLU specifically it goes from 0 to 1. For tan it's -1 to +1. So it limits the presence of how far it go. If we have negative infinity or the positive infinity, the computation would be much more expensive. It will the calculation would also be a bit more large. So no, NLTK is different thing. NLTK also NLTK we are using based on the data which is already been trained. NLTK is a module which is able to compute what we are saying. In NLTK, you can encode, decode the words. It's doing the same thing. These are the model hidden behind all our applications. Now we have looked into all those matters. Now comes the bidirectional. We have the single directional RNN. Why bidirectional came? So the issue was in cases where we have like for fill in the words, fill in the blanks. We process sentence, we have gap, and then further. Now, if you compute from the only single direction, after the blank, as per your data set is trained already, it will provide you that output. But that is also not highly accurate. It can be the mix of between two, and the model will choose something which is inappropriate for that current. So what we do is we compute from both the ends, from front and from back. We compute both together, and we have the answers. Now the output format are the different based on user case again, but out here what we are doing, we getting the output and then adding it to get the final output. And each stage we will get an output. So you can pass data set and get an output like sequential data, sequence to sequence. You provide one, you get one. And in this also bidirectional RNN and LSTM also we are processing in a sequence way, one after another. We are not doing parallelly till now. We are unable to use our parallel processing within our computers. Now, for more understanding on how the previously we had seen RNN, so this was our previous RNN, the same structure. What is happening? We are getting the output from this, where we are doing 1, 2, and from backend, adding all the data we had earlier forgotten it. We are neglecting all these outputs, but based now the situation is such that we need all these. So what we are doing output, and then this can be a node, or we can do simple addition of both the outputs. It's still something which we can train based on our requirement. Now there's another variation. We have a sequence to sequence, so every input will provide, every node is actually providing an output as correct. So there's another format which we can do. Yes. Okay, so back is not working. Okay. The animation. I need to change just a second. Yes.
Delete the one we already have.
No, not required. Yes. So So out here, now what we are doing is we are getting the output, collecting it at a node, and still we are having similar to this node, we are performing a similar operation. We have weights, all these input will be multiplied, taken the summation and add a number bias. We compute both, add and perform an addition here. So these are similar architecture behind it is the same, but based on our requirement, we will change as we go ahead. And this can be different for n implementations. You can implement however you like based on your requirement and client's implement requirement. Okay. Yes. So as we told, it has all the cons of RN and all itself, but being more computationally expensive. But RN works good on smaller data set, whereas LSTM requires a huge data set, really huge, in order for because of its computation. All the parameters needs to be adjusted, and it has. Okay.
Yes.
So it has all the cons, black box, we don't understand what is happening. And this will be present for all till the transformers also. We are unable to get what is happening there. Yes, it has become a bit opaque before we weren't able to understand anything, but we have gone some way advanced in that format. Now, computationally expensive, we have to, RNN is already computationally expensive since somewhat, and now we are processing twice. Now come the GRU. Now we have LSTM, RNN are also present. Why GRU? So LSTM we know is required high data set. The more the quantity of data, it will perform much better. So it will increase based on your data set again and again. But GRU comes in, it has less computations. If you can see, it has less number of gates. If yes, if you can see, the gates are reduced from 3 to 2. You can see. Operations are also reduced. The number of vectors required, the weights, everything has been cut down short from the previous version. So the main important impact GRU plays for the people with smaller data set needs to train their data set. And similar to earlier, in LSTM, if you notice, then let me go back. Yes, in LSTM, if you see, we were for this was the formatted. Now, whatever data we apply, it will get formatted. Some of it. It will depend on the computation as what is happening. But in GRU, we are only formatting and updating if we have formatting. If the data is not present or we have eliminated something, only then we will be adding it up. In LSTM, in whatever the case may be, we have formatting. Now, out here within the update gate, what we are doing here also, we are calculating what percentage of this data, the updated data, needs to be transferred. We provide the input, it computes. These all the data are from this current input. I have understand this, but all these data don't need to be updated. Only some amount is required to be updated as we already have data. And if you see, we don't have the cell state also, because we are dealing with smaller data sets. So we don't require high computation and thus the long memory cell state. So we are computing on the HT also. Now, why this? We move from RNN to LSTM. Then for people with small data set can use GRU, but why can't we use RNN also? So the problem with GRU, the RNN is that with weights, it affects it very much. In this case, we have less number of weights, thus, and we have multiple activation functions also. Okay, so the architecture is such that it won't let the model go out of control in search of weights. It will have it controlled. If the RNN gets controlled, we can also use it. But the RNN basic implementation of why we call it RNN is not able to do it. That's why we moved to LSTM and then GRU came. Now with GRU, when the GRU also came in the picture, we also came with sequential memory, encoder decoder. This was one of the groundbreaking, and this was the, we can say after this we have another operation within this that will give birth to transformers. Now we are still using LSD within this encoder. This block is called encoder, and this block is called decoder. The function earlier we were doing was providing input to LSTM and expecting output from it. But now what we're doing, we are providing the input to the LSTM, getting the cell state long memory and the short memory, combining it, as you can see, and then converting to context vector. Now this vector will pass down to the LSTM again. Now the thing happened was this part was able to focus its own a computation in analyzing what does this mean. The main computation was analyzing. It was able to understand what does mean means, two means, slice mean, and it was able to segregate those meanings much better than previous. There might be in previous algorithms in complex situation, it won't be able to differentiate what was the meaning between two things when they are in a certain order. It would provide you incorrect output. Whereas in encoder decoder, this was not the case. This LSTM was fully focused on converting nice what is. Now, as I earlier told you that these words can't be directly inputted. In all cases, we will use embedding, which will convert into vectors. Now we have all the data, it is learned. Now it's come for the prediction part. So at time of training, what we will do is, yes, at the time of training, this is our output block or the decoder block. What we will do is, we use teacher enforcing method, where whatever the output LSTM provides with provided input. Now the input start with SOS or start and end with end or SOS end state. So these are keywords which are provided to the model. So in order for it to start, what is the output? Now every LSTM will provide an output. It will then, as you can see here, the predicted output by one is this, but the true requirement was the above one. Now it is incorrect. What should we do? So we implemented teacher forcing method as to at a training point of time, whatever the output would be, we will neglect it, look aside and provide the actual output to the next. So if this node provides an incorrect output, no matters, don't need to look at it. Provide the correct input to the next node. Similar would be followed on for the other. And till the point we get an end. End means that the process is over. You don't need to process it again. Now, thing is, why teacher forcing method? It was we can use another method, but it would be more computational. Now you need to analyze this is incorrect. Now I need to correct it. So you need to use again computation. And by looking at this, is itself is a bit difficult to compute. So that's why we come up with the teacher enforcing method, which directly inputs the correct input and trains the model. Now, this won't be required at the time of when we say inference. At the output for when the model is trained, we don't require it. We can just provide the input. It has trained itself to what it needs to do based on our training model, teacher model. Now, still we had some issues like yes. So these context vectors are still from the previous day. Now, I was not told you that instead of LSM, you can use GRU or ANN. RNN, because the weight keeps it does not, it is unable to have a tie on its weights. It goes from one end to another, and computation and the key model keeps on learning itself, learning everything. It's unable to stop at a point. So the context vector is still of a fixed dimension, but we need more data. If the data is larger, we need to compute it within this cell. This dimension is fixed. Now, this dimension is fixed doesn't mean it is fixed as in like as per it's not fixed as in, but as per the training point of view. At the training point, whatever information is provided, like cell shape, all the parameters would be of same size. So these will also be of the same size. So these are fixed when by training. Now nothing can be done. So and because of this, when we have much larger data set, and we are going beyond the LSTM dataset point, we are going much bigger with the when we are getting the black hole today data. The data is huge with the internet and other things. So it's still getting smaller for our requirement. It's unable to have grasp everything within its context for it to decode. So we will have some sort of errors in the future. And if you can still see, we are using LSTM, we are doing sequentially. We are not implementing parallel processing here. The first will provide an input, output, then goes to next, and then encoder will provide an output to the other decoder. So still we are doing processes sequentially, not able to provide multiple inputs at a time. Yes.
So this encoder, we send nice to meet you altogether.
Yes.
And then in the decoder, is it a single output like Ravi, or is it like Ravi the rectangle?
No, it's happening sequentially. Sequentially.
Okay.
Start that it will convert nice, whatever we are requiring. Now this is another language. It's in German.
So that's fine.
Yes.
I mean, like, is it like nice to meet you, Ravi the rectangle?
Yes.
Something like that.
Now, if you convert in the previous models, if you convert nice, it will directly convert to nice. This is not a correct way of representing a thing. So it shift front and forth when we try to convert data into the different format. Grammar would change, everything will change.
One
Yes.
follow-up. These are changing weights, or I mean, like, are they prediction for the same thing?
Yes.
Okay.
So at the training point of time, we'll provide the input at
also
one at a
We
time.
are also providing the output as well, because it is
Yes.
learning.
At the point of learning, we need to provide both things.
This not learning. Right?
No, it's learning at the point because we have provided the bottom.
And output, bottom level. So now what will happen, I think based on this, the vector path will be generated all the way.
Now, this will be what happens when we train. We'll get an output.
Yeah.
This would be the first time stamp.
We discard the output. And
Yes. We are trying it to make it learn what we want.
It is actually like,
And
we are implementing so many things, but it is actually what is happening behind the scenes.
yes,
Yeah.
because now the data set is huge, so large that we are neglecting it. If the data set was smaller, we need to deal with the same data. But as we know, LSTM works with huge sort of data. So we are neglecting as there will be multiple interpretation of the same thing coming again and again in the data.
Oh, okay.
Yes.
Now I understand.
Yes.
So Ravi is not the name.
No.
Nice means Ravi.
Nice.
Yes.
That's what I was thinking.
No.
Yeah.
That is what I said, no? It is a different
It
language.
means that's thing. Another thing is that nice to meet you when we transform into another language, things will change. Nice won't mean Ravi.
आपको मिल गया अच्छा लगा, something like that.
Yes,
Oh, yeah.
yes. From English to Hindi, things will change. The word sequence would be changing. And earlier, we were able to do this. We were able to understand, as we already told you about LSP and RNN also we were able to do this. But the accuracy was not there. If we provide input, we will get like 10 times, within 10, we get like 2 outputs which are as per requirement, and we cannot provide this to our clients. That wasn't good thing and was not as accurate as we get to the encoder decoder. Now, out here, there's an issue also that we are providing these context vector issue still is there. Now, we came up with another model which is known as attention mechanism. It's the same thing, but thing takes a turn that we are not providing the context vector as it is. We are switching from this model where we are providing the LSTM with the output. All the data is collected at every point of time. The data will go. First of all, we will calculate all this.
We're also calculating backward, like bidirectional.
No, it's not. It has made some changes because all the data from here, the CT and HT will also go in there. So, and the person who made this made a bit changes. So it's still correct, but for basic understanding, we are going to the sequential because it's sequential to combustion. Now the data HT and CT similar to here will create a context vector, but rather than going directly into the decoder part, it will go into nodes which will be calculated. Now these still, but in basic context, these will be ANN will go, all the data will go, plus the initial states. Now, the previous state, first for is context vector. Now, from the second part, we also get another output that will go in all these outputs. And these nodes is similar number to the number of input. So, data from each LSTM will go within these nodes, plus data from the initial state after each decoding part will also come in here in each of these nodes. So we are not sending all the data now. We are not sending all the context vector. We are checking which or one of these LSTM outputs will impact in the formation of I, love, machine
So
learning.
the other ones will impact, it will have a lower impact. The first one, like the first node, it
Yes.
will have its own context vector, it will have a higher impact. The other nodes will have a lower impact, and that context vector will be used on that
Yes,
first one.
the ones whose context vector
Hmm.
would be much more like for let's take for the red part, we'll have the output from each node. Then we will have the CT and HT going here, and we will also have an input from its previous state. As in here, we don't have it, it would be 0, 0. But if we take after I, we have outputted I. Now I will also come in here for the next. So we have the data of what decoder has, context vector is there, plus the data of what the decoder part, what we have qualitative rate. So we have created I, now that will also come here. Then we will product below, then it will also come in here. So it has the context, what I have already done and what needs to be done further. Plus it will also calculate which one of these should be provided because the dimensionality is still fixed. We don't have n dimensional, we can't have in any case. So we are selecting which one is the best suitable for our next one with all the data, decoder, encoder, and all the CT and cell states.
That is why it is also called self-attention.
Yes, because it's providing now self-attention means we are converting. Yes, out here, we have created I. Now, in self-attention, what happens is your input and output, both languages are the same. Out here, this fully is not the self-attention. This part is the self-attention part. Self-attention takes place within same data set. We will provide I, then it will understand, okay, I is there. So it will happen with the both should be same. That's why it's self, analyzing itself, providing self-attention. What I have generated, now I will compute what I have generated. I will pay attention to it. I have produced this. These all are not required. Only this LSTM output or the second LSTM output, both are required for the next output prediction. That's why it is called self-attention.
This is from the paper.
Yes,
Attention.
yes. Now, after this, the bank, the more thing which we all know is transformers came. Now, I have purposefully kept the transformers, Optimus Prime, and this transformers as other than this encoder decoder, and when Prime is transformed into a truck, nothing is similar to us. All these things, when I will try to explain you more, you will understand nothing belongs from this world as per what we have discovered or we have created. So, okay. So, yes. Now, other than the encoder decoder, as a full observation from the not getting in depth is the same, but underneath nothing is the same. Similar to transformers, transformer prime, when C is transformed, you can't detect it on road. But when you get in depth to it, how is it working, what is the few energy structure of it, it's understandable of how it came into existence, because everything previous to it followed a route. It had something we meant behind faced some issue, so we implemented something for its betterment. What were the issues? We tackled it and performed new. RNN, NSTM, bidirectional RNN, encoder, decoder. All these were based on RNN itself. By tackling RNN's difficulties, whereas transformer is fully different. Nothing in here is similar to the previous thing. Other than the self-retention. Now, self-retention earlier was still sequential, but in mask head, we have multiple self-attentions. Now, I won't be able to explain everything of this, everything present here, because it will take an hour, because we need to understand what is multi-hand attention, what is mask, why we need feed forward, why we are skipping this part and providing data which needs to be converted, and uh, all these ones. And the other thing is transformers is parallelly possible. We can process parallelly rather than sequentially. And why we are able to do this? So positional encoding. Earlier we don't have positional encoding as a different thing. We provide one input, we get that yes, this is the first, then second. So we know what the sequence is. But when we process in transformers, we are providing the input, and positional encoding is a tag provided to each and everything. And each and every input provided has gotten a tag like this is the first, this is second, this is third.
And you're doing parallel processing, you
Yes.
don't know which one.
So we will process this parallelly, and this while processing parallelly, we don't have to care about which comes first, which comes second, which was the thinking behind sequential processing. So this provides an tag, we process it, and in the decoder part, it's able to detect which will come first and second based on its tag provided. So positional encoding, how are we implementing input is we created a vector, and positional encoding is in this format is using cosine similarity, so cosine function. So what we are doing, first input and first index of that. We use input in the sine cosine function, get the degree at which we will get, and that would be added to it. So we get a different number, and each number would get different representation as to what. And this position encoding itself is a great thing which they have discovered as to now we are using sine cosine. After every 90 degrees, they would be same. But after first node, second node, third node, first of all, we will have like in a vector, assume we have four dimensions. So sine cosine will be first. So we will fill the first two boxes with single input as one into sine one whatever degree we get, cos one whatever degree we get. We'll fill those first node, then second. In the second, what we will do is 1/2. The second input, whatever, if the position encoding is 1/2, next 1/3, and we'll get in pairs. Yes.
So between that, you have basically infinite numbers.
Yes.
That you will use for tagging purpose.
Yes, we will divide by each.
Who
So
came up with this? Like, do we have the names of people, or it was a
Yes,
collective thing?
it was a collective, around 6-7 people from different organizations were able to get it into. This came in 2017. Now, if you want to get more in depth, I've also just a sec. Not presentable. Just a sec.
There was a second one last time.
Cosine.
No. GDG one. He said like I haven't used math anyway. I would ask him to go through this one. Lucullus Chaturthi.
It's more of an applied.
Sharing.
This is more of the research here.
He's Angular actually.
Okay. Yes.
It's been shared with the King's processor.
No, I'm sharing. So it's taking. So I have created a block diagram as to how parallel processing is. Will not get in depth, just to see how actually data might flow with the structure of the data. Yes. If we go in depth, let's look at only the first part. So I have inputted who are you. Encoding will happen, perform into an encoded format where it will be 0 in some format. Now we will provide position encoding. Position in encoding is separate topic as I told you 9%, so we'll not go into this. But it will some provide some data to it as each every node that yes you are the first which came second third. Now all that data will go into the encoded part. Now we will have the data. We'll create, now this is the self-attention part. We'll get creating the blue matrix of size is also provided for each matrix. One is key, value, and query. So these will be the vectors. We will perform operations out here and get a scalar format. Then we perform scaling, softmax, and these are the weights after which we will be performing multiplication. So we get the final output. Now, this encoder part will be like eight types in every form, which can be changed. Each block which we see, you show have seen earlier. Hmm. Yes. So each block which you have seen out here will perform multiple times. And the output after the last block will go to the next part. So it was not like this is a single will happen. There will be multiple encoders in top of one another, which will perform. Yes, this will go sequentially, but the internal processing for the every node will happen parallelly. This text. Now, all this processing for this block, and the second encoding will happen parallelly. Everything in this part we are parallel processing some part. This is it is not fully parallel process, but yes, most of the data which are required to be parallel process, which are complex, we are able to do it easily. Now, this is earlier we were doing what this was single. We are performing in the why this is called multi-head attention is that we are providing attention to multiple heads separately. From this input, we are providing attention to it. What part should be included forward, and we are getting the output at the end. And these are the operation scaling, softmax, and linear transformation we are applying to keep things as per our requirement. Things don't go out of hand. The numbers stay within a range. As machine learning likes is continuous flow of data in decimal point, continuous flow within a range. If the range is bit more is larger, the computation will also take much more time. So we try to keep it from 0 to 1, or in cases -1 to 1. So this part is just the cell multi-head attention mechanism, the first block. Just yes, this is just this part. This small part required all that computation. Then we had forward, whereas if you can see, we are also applying a feed forward neural network, also known as ANN. We are providing ANN for basic computation behind this ANN was that to apply similar happened out here also. If you can see, this block is also an ANN because we the profit which we get from ANN is that we don't need to provide any sort of formula. How we are converting it, we don't need to know. We have ANN, it will do on its own. Or else it will take ages in order to get to a formula which will implicate the same thing. So researchers spend enough of your time in just getting to this part. But what they thought, now we have wasted so much, it has taken so much time. And one of the researchers came up that we have created AI, let's use it. And it was providing a fantastic result. So we kept it, and this is what self-attention is. Now, this was just the multi-head attention. Next goes to now the output we are here getting here. Let's cut out this. So you saw that there was a skip there. So in training part, we have a huge data set again. So there might be some errors made within this computation. So rather than again recomputing Yes, we will go back and forth again for error management. What is the error and updating all the weights which we have out here. But to tackle more difficult challenges, what we will provide the same output of here, the output which I have worked in and the encoded part will get combined. So any errors made within it would get compressed so that the next encoder layer, all this computation would not get hampered. So we are still having the touch of our previous data set and slowly and steadily getting involved how things should evolve slowly. We have a control over what is going on out here. And as also mentioned, we have around 6 more layers in this. The official transformers model has 6 iteration of encoder and decoder, and it can be increased to 8, 9, 10 as per the requirement. So for understanding how vectors convert, how are we encoded, who are we? This is the encoded format. We do not put these all are uh, firstly created at random and are getting updated as we go on. Yes, yes. And after getting the output from the encoder, we go to the decoder part, which also perform the same thing, but have bit different tasks than just decoding. Similar to encoder, but it has few features underneath its sleeves. So we are processing the same thing, but mass attention comes in. Now this implies is that while training, we need to process sequentially, but do we need to actually process say one at a time? So what we did was in mass attention, while training the data, our model has access to the previous correct output which is provided, which will come from here. Whatever the data needs to be, this is the correct prediction. Now, if we pass it on, all these nodes will know what data we have, but we process sequence in a parallel manner and one at a time, one block gets at a time. So what will hamper is that all these data will have actually cheated. They know what is going to come. So in order to do that, what we do is mass multiplication. What we do is at this point, we mask the data 0, 0 and negative infinity. And it goes to softmax function. What it does, it creates it will add such that all these data, the similarity search score, which we have calculated as to this part calculates how similar thing are. First, second, third, these words are. The first word, the second to third, all permutation combination as to what they are interrelated. This is what it is doing. Now, at this point, we have provided all the outputs, but we don't need. So what we do, we mask all these data. At the first point, we will also only get the first one. In the second, we'll get first and second. Third, we'll get all the data set. And we multiply it, the softmax, what it does, it reduces, eliminates, moves out, perform its zero application. So we are not cheating actually at the point of training. Now at the point of inference, we don't require it. So we also say transformers is auto-regressive at the point of inference, whereas is parallelly processing at the time of training. So we are saving how huge amount of data by doing this cheating. Or else we will need to still process it sequentially. Some format of data needs to be processed. One at a time will happen. Now, when we say parallel processing, only some part will be parallel and other things will happen in a sequential order. We can't process everything parallelly. So this is what mass attention helped us in training. We are skipping all the generation part and it's only it's able to understand what it is. Now comes to the next part, ANN, and we get to the final part of the data, our output. This is what transformers is. Now I all also have created added few topics which you might like to see is the MCP. Okay. Yes. So the hot topic currently working. So we'll see it in action when we will be not the NCP part, but why we require all this. I will be showing you in the coded format. So just for the basic idea, before NCP, this is our LLM, and we provide certain uh, tools for each. Like if you want to do web search, DuckDuckGo, you will add DuckDuckGo here, and the LLM will know, yes, if some things come up related to searching, it will use this tool. This tool will provide the output to the LLM. Now, all these nodes, when we create a huge software network, you will have n number of tools at your hand. Now, in order for you to maintain, all these things are privately owned. All these API provided by each separate entity. Now you have to manage it all. So in case you have 100, 200 tools, a company provides an update, your system will crash. So what MCP does is similar to how a cloud service provider works. It provides a cloud where it hosts all the servers and it manages it. And you just need to ask what are tools are required and your relevant users. So you need.
One question.
Yes.
For transformers.
Yes.
So we have, I guess, two main types of transformer, BERT and
BERTs and GPT are BERT is another form which developed by Google. Yes.
So like when do we select what kind of transformer we use when we work on it?
It depends on the company who are developed. Like ChatGPT works on transformer purely, but it has its own TOK. It's not the same, but the underlying structure is this. But they have developed something like for the similar DeepSeek. It was also working on the same architecture, but they have made few changes, knickknacks based on their requirement. Things would be same, just few things would be added.
They also
Few things would be
interesting, like this is the input.
Yes.
If it is in this output,
Yes.
so let us use this and create our model of the transformers.
Yes.
That is for the field.
Now, let's have a hands-on session on creating basic LLM as to how we can utilize. Okay. So first of all, if already we have a Python installed in our systems, then you are able to work. Or I was specially asked to work on local server, local LLM utilization. But in order for us to do that, we need to have Olama installed on our systems. You have both. So that would be much similar. So create new environment. Okay. Now for the setup, we will be using UV, which is the current new tool, which is much faster than pip installation. So yes. Okay. So first we need the pip installation of UV first.
This is all
Yes.
need to give us some time also.
Yes. Yes. Then now after UV in it, we can use after getting installation of UV, we can create our repositories using UV in it. It will create all the file structures for us. And as you can see, it didn't take any time as it's much faster than pip installation. Much, much, much faster. And it's more simpler. Now we need to create our environment. VENV. Our environment is completed. Now we need to activate. No, yes, our system is there. Now, also now if in order to add anything, we can use UV installation of any other packages, UV dot UV add and any package name like Jupyter Notebook. Done. Now we have created a file. Now there would be multiple dependencies which will be required. So let's create those.
So can we work with the column?
Yes, as currently we are not fully developing an end-to-end. We are just taking a brief of how to import, work on local LLMs present in our system. So now we first need LangChain, followed by LangChain community, LangChain core. Then, as we are working on Olama, and if anyone who is not having Olama, we can also use Grok API key.
I lost track. You have to wait if you can. I just completed. You
Yeah.
mean it.
Yeah, there's no issue. Now you need to use UV. Let me show you.
Let us go.
Yes, yes. So, okay.
If instead of UV, can I use
Yes.
the
Yes, yes. But you can compare the time limitation, how much time it would take.
right now?
Because as you can see, it created a Jupyter installation in 525 milliseconds.
Oh, okay, okay.
I'm using VNV along with UV. I installed UV inside VNV and then I'm using it.
Can
You can.
Yes, environment setup can be done from anything.
I don't want to install UV globally.
Yes, you can.
Okay, so I
UV sets up BNB for us?
Yes.
in this post you can do.
अच्छा तो Python dash m से भी कर सकते हैं.
Yes. You can use anything. I just wanted to show everyone how fast UV is, as I also tried. Earlier, you're always using either Conda for creating or pip,
Yes.
virtual environment.
UV at Jupyter notebook.
Yes.
What will it do?
It will add the Jupyter notebook. Or you can use UV add -r requirements.txt. It will load all the things.
But I don't have the requirements. I have to write this.
Yes, we will be not implementing full.
Okay.
We just taking the so because there are multiple requirements in order to make a full setup. So we'll be just taking a look how to use LLMs and create few simple tools.
Requirements for TXT is 19.
And
And you have to do UV install.
Huh?
For this requirement of TXT.
you can use direct pip installation also. There's no requirement.
What we have to do what before requirements?
Before requirements, you just need to set up your VNV, or you can use directly pip install Jupyter notebook or UV.
Can I edit in requirements?
Yes, yes.
UV will also be installed.
Because the book was
The UV is based on R language, so
compiler are the rest.
R. R or Rust, it's just,
Rust is that.
yes, it might.
Actual access. Rust.
Hmm.
Yes,
That, this is the comparison of how you use with the pip.
Not sure. I guess.
Olama nahi hai to, if Olama is not present, we can use LangChain Grok, and we can set up the Grok API key. You need to log into Grok Cloud. If Olama is present, you can work on that. There's no need.
okay, so I don't need grok and using
Yes, because Olama multiple like G models base are like 4 GB, so it will take time for us to install. So if it's not present, we can use Grok itself. So in Grok, if you need to create an API, you can go to create API, write anything about that, like, and then submit, and you will get a key and copy it. Now, let's start. So I will create a we will first learn how to use LLMs. Either if Olama is present, then well and good. We will use Olama present in our system for creating simple chatbot interaction with the LLM. So let's install. Select the kernel. Okay. Yes. Now in Olama, there are multiple ways of importing. Like this, another way. Uh, lang Olama import Olama LLM. But the best way of using is chat Olama because you can perform structural output in which in whatever way you require. If you need that output to be in structured way, like you want for some instance, you know the output in the form of client name and client number based on the data you have provided. So you can structure it so it will only provide when whatever you ask, it will provide client name and number only. Whereas when you use generally, it will provide as per the LLM's thinking. So now let's call chat Olama model. So you can use the model whichever you have pre-installed on your systems, and I will also show you how to use with the Grok. So and for people who are using Grok, you can chat Grok model, then Grok. Yes. Mhm. Model. Okay.
Okay, to use Java or any other model.
Yes, yes. Store.
That works.
I have installed, but
Because
okay, okay, okay,
from
okay. No.
Grok,
Yes, yes. Now in Grok, we can apply the API key in two different ways. First would be using the .env file. Uh, Let me show you an representation of how. So we can create an API key out here, specify in the same format .env. Uh, and for creating .env, you need to use the .env uh, load.env, and then in order to create, go to more. Yes, yes. You can directly pass the model name and the API key, or the another way is you can directly initialize within the Grok call also, API key like here. But it's more safer if you use within the .env because no one can read it. Yes, well, now our model is set up. We are able to call the models. Now let's use Olama. Olama dot invoke, and like now the Olama is functioning and it will provide us the desired output, which I think is the best. Yes. And now it will provide the AI message format as is provided by the AI. And if it's by the user, it will show user messages or directly messages based on the model, whichever you are using. And if we want a better way just to get the output itself, data, we will use dot context. Yes. Yes. Yes, now you can see we are just getting the output and all the data present, just again,
Direct input.
I'm doing where the input for asking.
Right.
so So, as you can see, all the data provided is in object-oriented format. It's not in a list or vector representation. It uses this format to get a better, easy access of data, or it would be high complicate. We will be complicating things. All the data, if you can see, is in the format of object-oriented. We have also used directly, or we might be, if it wasn't an object-oriented, we would be using AI message, then in brackets, what we need is the context, so it would be in dictionary format or JSON. So this is how we can use directly as a simple chatbot. But now let's make a few changes and create a prompt in which we can easily. Now, LangChain has its own way of creating prompts. Like we can also use chat prompt template and prompt template as per the requirement, but for easy, we don't need to import anything. We can directly use provided list. Within that, we need to provide a dictionary which will create the role. As in role, I will be providing this system with some message. Now providing the context or data. Con uh, Now the data would be input in whatever format we need, like you are yes. We can also use hub. Hub is used. We can import pre-existing prompts written within the what you see Hugging Face libraries. We can also directly use using hub. There are multiple ways of importing, creating prompts, but this is what I find the most suitable. But we can also use LangChain dot messages and human message or directly in this format. Also, we can provide. Now we'll add the role for user. Then content. Now I have created a variable query so we can have it a bit dynamic. Now what we'll do is use Olama dot invoke. Before this, we can have query equals to input enter your query. So taking an input from the user, invoke it and pass the prompt as in message. Now, if we run, we will get the output similarly. Yes. Oh, yes. Now, yes. Now let's run. I'm asking the full form of LLM. Context to ML. Now it will generate the output, and if we do print data.context will get the output. Now see, it's unable to, okay, I haven't, yes, query variable markup, yes. Yes, yes, this is how the output will be. Now, this prompt can be from 100 lines to 200 lines as per our requirement. For context, uh, just a sec. Structure. Yes. These are few of the prompts which I have written for one of my applications. So these can be of any type, any format, whichever you want. And similarly, you can use either roles or directly AI messages as per your liking. Now for OLAMA specifically, I would recommend you to use the chat OLAMA model, because in case of structured output, yes,
We're actually running a bit out of time.
yes,
We can open up for breakfast or just we continue further.
Okay. Okay.
Is it okay?
yes,
Is that
yes.
okay by you?
Uh,
Let's do that. Hands on, ये लोगों को करो, वैसे करो,